This is some examples of sea level rise in the news. So Venice, 2019, there was a major event of sea level rise. The rise was 1 meter and 87 centimeters, so almost 2 meters. This is the highest sea level rise they've had in 50 years, and it flooded a significant amount of the city. And then on top here, you see Fiji. Here's the location of Fiji on the map, where there's an ancient burial site, and you can see that what used to be land now is clearly flooded by the ocean. So these are two examples of sea level rise that you could see in the New York Times and The Guardian. Okay, here's another one. This is from the New York Times, an opinion piece called Swallowed by the Sea, and this says, "You doubt climate change, come to this island, but hurry before it disappears." And this is this person standing on that Kutubia beach. I'll show you where that is in a second, pointing to where his house was and where his fields were before this sea level rise that he encountered in his own lifetime. So where is this? This is Kutubia Beach, so it's an island off the coast of Bangladesh. Here's the island in a zoom in. And so let's see, this person is how old do you think? 70, between 40 and 70. So suppose this person has experienced sea level rise over the last 30 years. How much did sea level rise increase over the last 30 years? Well, the rate right now is 3.5 millimeters times 30 years. What would that give us?
100.
So this is 3.5 millimeters per year. In 10 years, it would be 3.5 centimeters. In 30 years, it would be about 10 centimeters. Would that be enough to flood the home and fields of this person? Maybe not. So something is going on here, and we need to understand why and what. Okay? Make sense? Great. Now, solutions for sea level rise. Even before we know what the magnitude of the problem is, here's an idea to close the North Sea. So you build a wall here, and you build a wall here, and therefore all of this area here is now protected from sea level rise, which is kind of nice. There are examples of things like that. This is the seawall in South Korea and another one in the Netherlands where people actually build such significant obstacles, although the ones that will be need to build, of course, are much more significant. But these are the ideas that people come up with. In Boston itself, here's how we're going to protect the Boston harbor by building this wall around it and so on, and protect Boston from sea level rise. All right. Let's talk about some definitions. So this is going to be important today. So relative sea level. Let's draw this. Here's the coast. And here's the ocean. And relative sea level is the distance from the surface to the bottom. This is relative sea level. Global mean sea level is basically a measure of the volume of the ocean. So the idea with relative sea level is if the wind blows, relative sea level could rise here and decrease here because the water shifts from one place to another. But global mean sea level is not sensitive to just shifts of water from one place to another. It's a more robust quantity that is a measure of the volume of the water in the ocean. So that's global mean sea level. And then another term that we'll see quite a bit is thermostatic sea level change. That is the sea level change due to changes in the temperature of the ocean. So if the ocean warms, sea level expands. We'll talk about that a lot. And the expansion of seawater leads to sea level rise, even without melting of ice or anything, right? Just the expansion of seawater with temperature. Here's a map of sea level rise, local sea level rise. So this is the rate of increase from 1993 to 2012, so a period of about, 20 years. And you could see how varied this is from place to place. So we talked about global mean sea level rising right now by 3.5 millimeters per year. But if you look locally, it goes anywhere from a decrease of a few millimeters per year to an increase of 10 or more millimeters per year. So there's a very large variation, local variation, in relative sea level or in the sea level increase locally as opposed to the global mean sea level. of course, people live in specific geographic places, so whether you live in San Francisco or in Manila, your experience of sea level rise is going to be very different. Look at this. San Francisco is seeing a decrease or a stable sea level, while Manila is seeing a significant increase. So there are two things we need to understand. Why are there such strong variations from place to place? What's causing it? And what is their connection to anthropogenic climate change? So, okay, how do we observe sea level? And start from the basics. It used to be that there's a tide gauge, there's a float here that measures the level of the ocean at this point, and it's connected by a wire to something that then has a pencil writing what the elevation is. Today, it's obviously different. You have some instrument that measures the travel time from a certain point to the surface of the sea, and it's much more accurate and much more higher frequency in time, and is done electronically without any moving parts, so it's much more reliable. Another thing we could do is measure the pressure at the bottom of the sea. So if I measure the pressure here, if I have more water above me, then the pressure would be higher. So the pressure at the bottom is an indication of what the relative sea level is at that point. So this is an example of a seafloor tide gauge that measures the pressure and is a very important source of information of sea level and its changes. Okay, of course we have satellites. So there's a type of satellites known as altimeters. Here's an altimeter. It sends an electromagnetic wave to the surface. It's reflected. You measure the travel time back and forth. And from that travel time, you find what is the distance between the satellite to the sea surface height. And from that, you know the sea surface height. And this is a global measurement because this satellite then travels around the globe and makes a measurement like that everywhere in 10 days to 2 weeks, roughly. So that's obviously new only in the last few decades. And then you have this geologic evidence. So you go to this place in Arctic Canada, and you clearly see that the shoreline was in a different place. So if you manage to find a way to date when was the ocean at this point, then you have a point that tells you sea level was higher by a certain amount at that time. You just need to be able to date these terraces, essentially. So we could always also find old corals that used to live close to the ocean surface and date them. So there's this geologic evidence that we can use to figure out what sea level was, 1,000 years ago, 20,000 years ago, and so on. What does this tell us about when did sea level start? Here, let's look at even this one. Based on this record, when did sea level rise begin?
Maybe around 1800?
1800. When did CO2 begin to rise significantly? 1850. So it looks like the sea level rise starts early. Does anyone know what is the reason for that?
Maybe coming out of the little ice age.
Yeah, so there was a little ice age, a naturally occurring climate cooling. And then when we started getting out of that, around 1800 or before, ice started melting, sea level started rising, and then anthropogenic warming happened and accelerated the sea level rise as a result of that. So not everything you see here is a result of anthropogenic warming, but at this point, much of it definitely is, if not most of it. This is a measurement from satellites that's pretty accurate, and you could see that they detect the signal due to the cooling due to Pinatubo and due to El Nino and so on. And generally, the current sea level rise based on this is 3.5 millimeters per year, which in 100 years will give us 35 centimeters, but it might accelerate, of course, and we'll talk about that. Okay, here's the rate of change of sea level. If you're a climate skeptic, you would emphasize the fact that the sea level rise rate of change has been higher in the 1940s by this estimate, not necessarily by these estimates. But basically what this tells us is that sea level naturally goes up and down. Of course, if you look at this carefully, you see that all of the values are positive here. So it's only the rate of change that goes up and down. The sea level is actually always increasing in this period that we're talking about. If you read articles by climate skeptics, they emphasize the fact that the rate of increase is going up and down, and maybe right now isn't the highest rate that ever happened, but in fact, sea level has been increasing consistently over a long time now, for many decades. And we'll see an analysis of the time scales in which it's increasing and so on shortly. And remember, we asked before, by how much did it increase? So you see it here in millimeters. So it started here and it went up to here, so about 25 centimeters. I think someone did say 25 centimeters for the, thank you for that. What's your name? Megan. Okay. So the increase we've seen so far is about 25 centimeters. And let's look at the projections now. So let's start with the worst case scenario. Business as usual, 8.5 watts per meter square radiative forcing. So RCP 8.5. And the total increase is this curve with the gray arrow bar. And you can see that the largest bound on the arrow bar is about 1 meter by the end of this century. By 2100, the worst case scenario, the highest arrow bar there is about 1 meter. There are scenarios that are even worse than that, but I think this is sort of a midway worst case scenario. 1 meter is the most that we can anticipate. It's a lot in some places. But it's good to know that. Now, if you look at the components of this, let's see. So the red one is due to the thermal expansion. We're going to talk about each of these components separately. The melting of glaciers is indicated by the cyan line. The Greenland and Antarctic ice sheet contribution is here, and so on and so forth. So this gives you an idea, and you can see that the strongest contribution is the expansion of seawater due to warming, which we'll talk about just now. And then after that, it's glaciers and Antarctica and Greenland melting. That's expected by 2100. Some idea of the regional pattern of sea level rise. So we looked at this before, and you can see that in different areas, you have very different trends. So while the global trend is 3.5 millimeters per year, you see this area in the Pacific versus this area in the West Pacific versus the East Pacific. You can see a very big regional variation of sea level rise, the rate of change. So we have to know where we are in order to know by how much it's increasing. Look at this time series. So you see the global mean curve is the red line. Look at Stockholm. It's showing a decrease with very large variability. Manila is showing an even stronger increase than the global mean. Some places are pretty close to the global mean. Okay, so now we're going to start going over all of the processes that lead to sea level change. So let me just give you a one sentence per each, and then we'll start going over each of them separately. So thermal expansion we talked about. The ocean warms. As a result of that, the water expands. If the water expands, sea level rises. Glacier melting obviously adds water to the ocean, so that leads to sea level rise. Land water storage. So if we build a dam and block water from flowing into the ocean, this would lead to a decrease in sea level, right? Coastal erosion. If the beach is being washed by waves or by storm, this would lead to an increase in sea level rise. Think about relative sea level rise. You're washing the shore away. Relative sea level increases. And then there's everything that has to do with the interaction between the ocean and atmosphere. So this is an important part of the business. So we have atmospheric pressure, wind stress, and ocean circulation. We'll talk about all of the above. And then gravitational effects. That is so if Greenland melts, it turns out that the ice mass over Greenland attracts water, ocean water around it. And if it melts, that affects that attraction, and that affects sea level remotely and near Greenland. And we'll talk about that. So these are the factors we're going to be covering today. Well, let's start with thermal expansion. Remember, we went through the greenhouse effect last time, and the greenhouse gases trap a certain amount of radiation, say 4 watts per meter square for doubling of CO2, as we remember from last time. Where is that heat going to is what this graph is trying to show, and you can see that the two blue parts are the upper ocean and the deep ocean, and that takes 90 to 95% of the heat that is trapped by greenhouse gases goes into the ocean, and that is what leads to sea level rise. There are other components, but it's basically the ocean is absorbing the heat. Okay, so now if we look at this, you see the spatial pattern of the absorption of heat by the upper 700 meters in panel A. And then you see the latitudinal structure of this absorption. You see there are variations from place to place. So the warming in the ocean is far from being uniform. Some latitudes heat more, some latitudes heat less. some depths hit more, and some less. Okay, so, and that's going to be important when we try to calculate sea level rise. Where the heating happens is going to make a big difference. We'll do the calculation in 1 second. And this shows us the heating as function of depth and time. So you see that the temperature was relatively cold. This is the temperature anomaly, so it starts at minus 0.3 in some places, and then you see the warming with decades at all depth levels up to 700. Of course, there's warming even below that, but it's weaker. The deeper you go, the less warming you get, because it takes time for the ocean to mix the heating down to the deep ocean. That can take decades and hundreds of years and even more. As I said, if the ocean water being warmed is cold or warm makes a big difference as to how much effect this has on sea level rise. So we need to know what the temperature in the ocean looks like as a function of location. So first of all, as a function of depth, here's a typical profile in the ocean, profile of temperature. So the upper part of the ocean, the temperature is well mixed. You see this vertical line here. The reason is that this upper part of, say, 50 meters, or depends, could be more or less, is well mixed by waves and so on, and therefore the temperature is uniform. And then you starts decreasing the temperature. This area of decrease is called the thermocline, and then you go into the deep ocean where the temperature is very, very weakly varying, so the temperature is almost uniform there. So this is a typical profile. It's sort of exponential-like. Okay, now if you look at different latitudes, so here's a measurement across the Atlantic Ocean. The right side is the north, is close to the North Pole. You see this is 60 degrees north, and this is 70 degrees south, and the vertical axis is depth going from the surface to 6 kilometers. So what do we see? The most obvious thing is this cold water coming from Antarctica and sinking and spreading north and getting stuck at this topographic feature at the bottom of the ocean. And then there's also a similar sinking of water from the North Atlantic that is more difficult to see. It's basically this area right here. And you can see that indeed the deep ocean is colder, as we see on the right, but there's also latitudinal variations, and of course there are longitudinal variations of the temperature as well. Okay, so here's the explanation basically. So we're talking about this process right here. The temperature increases, temperature of the ocean increases. The density as a result of that decreases. Now, if the density decreases, the volume occupied by the same water mass is larger, and as a result of that, sea level rises. Now, let's look at two situations. So suppose we have water. So what do we see here? This is temperature, and this is the salt concentration of the ocean. So this axis, and you can see that the salinity in the ocean typically varies from 33 to 36 or something like that. So it's roughly 35 parts per thousand. Okay. The density of seawater depends on both the temperature and salinity, okay, on the salt concentration. Of course, fresh water is lighter and warm water is lighter. So now let's suppose that because warming, that changes the density by 0.001. So look at this thing right here. The temperature was, right here, was about 14 degrees, and I warmed it to about 18 degrees, so about from 13 to 18, so about 5-degree warming. And the contours are contours of the density of the ocean water. So the density changed from 1.260 to 1.250. And these numbers would be ton per meter cube. Okay? So this is how much warming is needed to change the density by this amount. Now, suppose the water is much colder. So we're talking about taking water that is minus 2 degrees. The freezing temperature of seawater is minus 1.8 degrees Celsius. So we take that water and warm it by 10 degrees, and that causes the same effect on the density of 0.001 in these units of ton per meter cube. So the amount of heating, of warming that's required to change the density by the same amount depends on the original temperature of the water. A 5-degree warming here would give me a certain density change, but 5 degrees there would give me a bigger density change. Bigger density change means more sea level rise. Okay? So therefore, if you warm warm water, you get more volume change and sea level rise than if you warm cold water. Make sense? So let's try now to go through the simple calculation of how much sea level rise are we getting for certain warming depending on what the density or temperature of the water is to begin with. Okay, let's start. We'll do this in 2 steps. First, let's take a simple back-of-the-envelope calculation that will give us an idea of how the sea level rises due to warming. So let's consider a water column whose depth is, say, d0, is the vertical extent. So this is the up direction, and we have a vertical extent. d0 could be 1 meter, could be 100 meters, never mind. And the temperature is T0 of this thing, and then we're warming it. So now the distance is d, and it's slightly higher. The column of water is a bit higher. And the temperature now is T equal T0 plus delta T. So we warmed the water column, and it expanded, and the new height is d, while it was d0 before. As we do this, the one thing that doesn't change is the mass of water. So let's write mass conservation for this thing. So we can write the mass is equal to d0 times the density of T0, and it's also equal to d times the density rho of T plus T0. This is the mass conservation for the warmed fluid element. So this is the mass per unit area. To get the actual mass, I need to multiply it by the horizontal area as well. We don't need to do that. That doesn't change in this scenario. Okay. So this means that d, the new height, is equal to d0 times rho of T0 divided by rho of T0 plus delta T. And as a result of that, we have that the sea level rise is d minus d0, and that's going to be equal to d0 times rho of T0 divided by rho of T0 plus delta T minus 1, which I can write as d0 times rho of T0 minus rho of T0 plus delta T divided by this same thing. And I finally set it to delta rho, which is the change in density, divided by some rho 0. So the numbers we're talking about here are 1020. Okay. So I'll show in a second that the density change is so small that I can replace the denominator with a reference density that is constant. We'll do this in a numerical example in a second. So the final step is that the sea level rise, delta D, is proportional to D0, the depth to which the warming penetrated, the extent of height that was warmed, times the density difference divided by some reference density that is a constant number. Okay, let's do a numerical example. So suppose T0, example, T0 is 16 degrees Celsius. Suppose delta T is roughly 3 degrees, and suppose D0 is 500 meters. So what we have here is relatively warm water. One second. Relatively warm water being warmed by 3 degrees, and the warming penetrated from the surface all the way to a depth of 500 meters. What is the sea level rise as a result of that? So we can calculate it easily now, because in this case, let's see, rho of 16 degrees is 1025.75. Rho of 19 degrees is equal to 1025.75. 0 to 2. This would be kilogram per meter cube. So we can calculate delta rho, the difference between these, multiply it by d0 and divide by rho 0. So as a result of that, we'll find that delta D is equal to 35 centimeters approximately in this example. Okay, so this was a rough estimate. Now we don't know how these densities are calculated. I just gave you the numbers. But what you can see here is that the changes are very small. Look at this. We changed it in the 1, 2, 3, 4, fifth significant point. So the changes in density are very small. But because this is proportional to the depth in which this happens, D0 enters, which is 500 meters in our example, then even a small change in density leads to a significant sea level rise. So now that we have this back of the envelope calculation, let's see how we actually calculate sea level rise for the more general case where the temperature varies from place to place as we saw and so on. So calculating a global mean sea level rise. So the first step is to calculate the change in the volume of the ocean due to the warming, and then we'll divide that by the area and get the sea level rise itself. So the change in the volume, delta V, is going to be, I'm basically taking this calculation here and applying it generally to the ocean in the following way. Let me write it down and then I'll explain what we did. So we have an integral over x, so that would be the east-west direction, and then we have an integral over the y, which is the north-south direction. And then we have an integral from the bottom of the ocean minus h to the surface, 0, of delta rho divided by rho 0. And this is delta rho of x, y, and z times dz. Z is up, so this is up. Okay. So we're integrating over all three dimensions. And if you're all done, so let's see. This part right here is exactly what we had before. The only difference is now I'm looking at a small increment in the vertical direction. This replaces our d0 before. Now it's a small dz. That small dz changed its density by delta rho. We divide it by rho 0. So this part is the change in the height of a water element that used to be dz. Now it's dz times this. So the change to that is dz times this. That's the change in the height of this small element. Now we integrate over all depths, and we integrate over the horizontal dimensions, and we get the change in the volume of the ocean due to the change in density at each location. And now we need to refer this to the change in temperature, which is actually what we're interested in. Questions? Yes?
What's negative h?
Minus h is the bottom of the ocean. So we're integrating from the bottom of the ocean to the surface. So given this change in volume, we can calculate the average change to the global mean sea level. To do that, we need to talk about something known as the equation of state. So we need a relation between the density and the temperature. So we can write the density of seawater as function of the temperature and the salinity. Temperature is T is the temperature of seawater, and S is the salinity. Let's suppose the salinity is constant for this purpose right now. So we just set it to some S0. So that would be equal approximately to some density, reference density. So constant reference density times 1 minus alpha T times T minus T0. So this is an equation for the density given the temperature. Where alpha T is defined to be minus 1 over rho 0 d rho dt, evaluated at some T0. Okay, let's see why this makes sense. What happens if the temperature increases? What happens to the density here? It will decrease because of this minus sign. Alpha itself is a positive number, so this is larger than 0. And therefore, as the temperature increases, the density decreases, which we know is the case, right? So it's a simple relation between the temperature and the density, which is what we needed. So now let's call this thing right here, this sign right here. So let's see. We have delta V. The change in global mean sea level is equal to delta V divided by the area of the ocean. Okay? So now we can take that expression and write it in the following way. So that would be equal to the 1 over area times the integral dx, integral dy, integral dz of alpha t times delta t of xyz dz, where I use that equation of state to write that delta rho, which is equal to rho of T0 minus rho of T0 minus plus delta T, is equal to rho 0 alpha T times delta T. So I use that. So this is the delta global mean sea level. We can frame this. This is something you will be able to use now in your calculations to calculate sea level rise from changes in temperature. You'll be given what alpha is. And remember, alpha, this is the expansion coefficient. The value of the expansion coefficient does depend on the temperature. It's not a constant. Okay? Let's continue now to ice sheets. So what do we need to learn about ice sheets and sea level rise? Clearly, if ice in Greenland and Antarctica melts or mountain glaciers melt, then sea level will rise. So let's see what it is that we can say about that. So here's the mass loss from Greenland. The map shows you where the mass loss happened over the last few decades. So this is since 2002. And the curve shows you the cumulative mass loss. So this is given in units of gigatons. That's not very helpful, perhaps. But at the bottom, it says here that global mean sea level rise due to Greenland was recently about 0.4 millimeters per year, and from Antarctica, 0.3 millimeters per year. Remember, we're talking 3.5 millimeters per year, the total. So together, these would be about 0.7, which is a non-negligible fraction of the global sea level rise per year. Okay, so this is what happens in Greenland, and this is Antarctica. Also loses a mass consistently over this period, and this is the area in which it loses mass. Notice the blue parts here. Blue means that Antarctica is gaining mass as opposed to losing mass. Why would Antarctica be gaining mass now? So suppose we've had some warming already. Can you think of a reason for why increase in temperature would lead to Antarctica gaining? Yes? Yeah, if the air is warmer, there's more moisture in the air, therefore there would be a larger snowfall, and Antarctica might gain some mass as a result of that. But you could see that the net right now is Antarctica is losing mass. Now, ice sheet processes are extremely slow, hundreds of years at least, if not slower. we can't tell for sure whether the decrease we see in the mass of both Antarctica and Greenland right now is indeed related to anthropogenic global warming. It's difficult to say right now. But we have observed them both to lose mass in the last couple of decades. Okay. Here's something more general about Greenland and Antarctica. So let's start with Greenland. You have an ice sheet. The upper part of the ice sheet is where accumulation happens. You see the green part right here. And the lower part is the ablation zone. Ablation means losing ice. It could be due to melting. It could be because the ice is flowing into the ocean. It could be because ice is breaking from the edge of the ice sheet and is floating in the ocean. Anything like that would lead to ablation. So Greenland has on its margins areas that are losing mass due to melting, and on top of Greenland you're getting accumulation. So this is the accumulation zone and the ablation zone in Greenland. Antarctica is different. Antarctica is colder, so there's no ablation due to melting in Antarctica. Instead, the ice flows from Antarctica to the ocean where it floats as an ice shelf. The thickness of an ice shelf could be 500 meters or even a kilometer, and that eventually ice shelf is breaking parts into the ocean and losing mass that way. So they're both in equilibrium in general, before anthropogenic global warming, in the sense that the accumulation is balanced by ablation in both of them, ablation being melting in Greenland and ice flow in Antarctica. That's the normal equilibrium. And if we increase the temperature, we can change that equilibrium, either by increasing accumulation or by melting, and we'll see which one wins in a second. So here's a typical schematic discussing the changes in accumulation, ablation, and net mass balance of an ice sheet. So let's start with the obvious. The red shows us the rate of ablation. So this is the rate at which an ice sheet loses mass with temperatures. So if the temperature is very negative, there's no loss of mass due to melting, essentially. This is okay. And then when the temperature increases, melting is enhanced and you're losing a lot of ice. Accumulation also changes with temperatures. So as the temperature increases, this is the blue line. As the temperature increases initially, there's more and more snowfall and this increases. At some point, if the warming is enough, the accumulation could be in terms of rain instead of snow, and that may not hold on the ice. That may flow off the ice and not stay there. In addition to that, you get more, so you're actually losing accumulation and it's going down because of this issue of the precipitation falling as rain instead of as snow, and eventually you're going to zero accumulation. If you look at the net, which is accumulation minus ablation, then you see that the net is increasing with temperature for a while, and then it's decreasing and the mass loss due to the high temperatures dominate. Now, Antarctica and Greenland are in two different places on this curve. Greenland is close to the part where the net is decreasing with temperature. So as we increase the temperature, Greenland is expected to immediately lose mass, while Antarctica is somewhere here. So as we increase temperature, initially Antarctica is expected to grow and only later to start lose net mass. Okay, this takes us to mountain glaciers. We'll do this briefly because we do have a chapter about mountain glaciers. So here's the classic example of before and after. So this is 2006 on the left, 2015 on the right, same glacier in Switzerland. Take the picture taken from basically the same point, and you can see a big difference. Where there was ice then, there's a terminal lake now. And if you click on this link here, you'll see many more pictures like that. There's no question that mountain glaciers are retreating almost universally everywhere in the world very dramatically, and there's no question that melting of glaciers right now is driven by anthropogenic global warming. Some of the retreat 100 years ago might have been natural due to the exit from the Little Ice Age, but currently the glaciers are melting with a very high probability due to global warming that is induced by human greenhouse gases. Okay. What does this mean to global mean sea level? Approximately, all glaciers excluding Antarctica and Greenland, so mountain glaciers away from the ice sheet, gives us about 0.8 millimeters per year. So it's again a significant contribution. Okay. Again, we're keeping this short because we'll talk about mountain glaciers a lot later. Okay, let's move on to the next one, coastal erosion. This is this picture in the New York Times. What happened there? This is from this paper. You get a description that in 2012 there was a significant coastal erosion due to tidal waves, winds, and heavy rainfall that lasted a few days and washed much of the shore and led to an increase in relative sea level because of the coastal erosion. So sea level, the absolute sea level did not increase, it's just that the land was eroded, and that led to the loss of houses and agricultural area. Now, it's possible, of course, that the significant rains or storm that led to this is due to global warming, but that the attribution there, the being able to tell that that event is due to anthropogenic climate change is a more difficult task. And we can't do that with certainty right now. Okay, here's another picture of coastal erosion, this time in New Jersey. So look at this area here. This is 2009. And look at this stretch of coast here, and look at this same picture, 2012. You can see that the coast is much narrower. So again, an example of coastal erosion due to a significant waves and stormy conditions. Here's another dramatic one. Let's skip all of these because they're the same. Look at this one. The houses are really hanging over the cliff. The cliff is eroding. So it's another example of coastal erosion, in this case a bit more dramatic because it's a cliff and all that. Okay, great. Moving on to water storage. So we mentioned water storage before. Here's a graph. So here's an example of a dam. You build a dam like this, a dramatic dam like that. You keep water that would have flowed into the ocean, and therefore the sea level would drop as a result of building dams like that. So if you look at this curve, this is the change due to ice sheet and land water storage. So you can see sea level dropping by 5 to 10 millimeters from 1950 to 1980 or so due to the building of dams. But then there's overpumping of groundwater that compensates for that, and that leads to this growth here. And you have this comparison of the orange curve is simply the land water mass, the land water storage. These curves give you the contribution to due to Greenland and Antarctica, so that you can compare, and you can see that the storage of water by building dams and then the overpumping of groundwater has a significant effect to that of melting in Greenland and Antarctica. So it's a pretty dramatic effect, and you can see that it reversed as we moved from land storage to overpumping groundwater in many places in the world. Okay, this one is a bit more evolved, so we'll do this in several steps. So it's really 3 different subjects. We need to worry about atmospheric pressure, wind stress, and ocean circulation. 3 different processes that lead to a significant variation of local sea level. And we saw before how strong local variations in sea level are, and these are the main effects that lead to that. So let's go one by one. We'll start with atmospheric pressure. So first of all, if you have a hurricane, you know that there's low pressure in the center of a hurricane, right? It turns out that, let's look at this one. This is Hurricane Katrina. The central pressure is 220 millibar at the surface in the center of the hurricane, while around it, it's 1,010 millibar. The difference between the two is 90 millibar. If you have 90 millibar difference over the ocean, that would lead to a sea level difference between the center of the hurricane and the margins of 90 centimeters. So it's 1 centimeter per millibar. And I'll try to explain how we calculate that and what it exactly means. But basically, if you have a hurricane and low sea level pressure, this would lead to a rise in sea level height and in the center of the hurricane. So let's see how we do this calculation. So sea level pressure and sea surface height. SSH is sea surface height. So here's the scenario we're looking at. This is up. This is the surface of the ocean. And we had initially a situation where the sea level pressure was the same everywhere. So this is the atmosphere here and the ocean here, okay? And we moved into this new situation where there's a drop in sea level pressure or a higher sea level pressure in this case. So now we have the pressure here is P plus delta P. The pressure here is still P. The pressure here is still P. And in this case, the pressure was P everywhere. So we moved from a situation of a uniform sea level pressure P to a place where there's a center with a higher sea level pressure. And we want to see, so the plot itself already shows you that there's a decrease in sea level. We want to calculate how much that would be. And of course, if there's a decrease in sea level pressure, then that there would be a rise in sea surface height. So let's see how we come up with that. So the idea is this. Let's call this delta H. And you could imagine that if you increase the sea level pressure somewhere, then there's a higher pressure here than here, and the water would flow from high pressure to low pressure, right? Okay. So the idea of the calculation is this. We're looking at this point and this point, and this point and this point. So somewhere at some depth in the ocean here, there's a pressure, the atmospheric pressure, and there's the same thickness of water above these 2 points, and the pressure inside the ocean is the same at this point. But here, before the sea level changed, there was a higher pressure here than here. So there was a flow from this area to this area, and the flow stopped when the pressure is again the same. Okay, so I can delete this arrow. So I'm looking for how much sea level do we need to drop here so that the pressure under this point is the same as the pressure under that point. So what is the change in pressure due to this change in sea level height? So change in pressure at point 1 due to the change in sea level height delta H. Well, the change, this would be the change in the weight of water above this point 1. So that's going to be equal to delta H times the gravity times the density of water. That is the change in pressure at point 1 due to the drop in sea level height. And we want that to exactly balance the delta P due to the atmospheric pressure. So we can write change in pressure in point 1 due to atmospheric surface pressure plus change due to sea surface height change should be equal to 0. This is the balance. Because we want eventually the pressure at 1 to be exactly as the pressure in 2, which is the unperturbed pressure. At that point, there won't be any water flow anymore, and we have the new equilibrium. So if we write this in terms of an equation, then it looks like this. Delta P, the atmospheric part, plus rho G delta H is equal to 0. So that tells us that delta H is equal to minus delta P divided by rho G. So this is sea level changes, sea level change due to atmospheric sea level pressure, SLP, change. That's what we were looking for. That answers your question from before. So I'll give you a second and we'll think about this now. So let's substitute numbers. Example. So if delta P is equal to 50 millibar, that's basically 50 hectopascal. That's equal to 5,000 Pascal. And that means that delta H is equal to, let's see, so 5,000 divided by the density of seawater we now know is 1,025 roughly, and G is roughly 9.8. So this would give us 50 meters. So we found that 50 millibar, 50 hectopascal, reasonable signal of a strong hurricane, can give us 50 centimeter. Terrible. 50 centimeter, right? So the low pressure at the center of the hurricane can give us 50 centimeter sea level rise. That, together with storm surges and so on, makes a big difference. So that's one significant effect of atmospheric storms is the low pressure at the center of these storms. So a reminder, we're talking about these atmospheric and ocean processes. So the first one was atmospheric pressure. The next one is wind stress. That is the reason for the Venice flooding. So let's look at this to remind ourselves. This is what it looked like in Venice. Why does that happen? So here's Italy. Here's the Adriatic Sea right here. This water body is the Adriatic Sea. Suppose the wind blows basically from south to north over the Adriatic Sea. It will push the water toward Venice. See, Venice is right here, and sea level will rise. So this has nothing to do with the warming of the ocean and expanding of seawater or, anything else. It's local storm conditions that can lead to that. Last time this happened was in the 60s, I believe, was a similar event, but it's pretty rare. Now, of course, it's possible that anthropogenic climate change makes these rare events less rare, and then that would be a contribution to sea level in Venice due to anthropogenic climate change. Right now, we don't know whether that event 2 or 3 years ago was due to anthropogenic climate change, but it's important to understand how it happens because it's a good example of how wind stress can affect sea level rise. So our objective is to calculate, given the strength of the wind push over the ocean, the wind stress, if you want, that's the force exerted by the wind over the ocean, the frictional force, the drag of the water by the wind. Given that, how much sea level rise are we going to get? That's the calculation we're going to do next. This is the configuration, so you might want to put this into your notes. I'll try to reproduce it here. So wind stress and sea surface height. So here's the Adriatic Sea. This is north, this is south, this is sea level. The wind in pushing things in this direction. As a result of the push by the wind, there's more water here than here. And because of that, there would be a pressure, there would be high pressure here. And low pressure here. And by that I mean pressure inside the ocean at some level. And because there's a high pressure here and low pressure here, there would be a force, a pressure force. So this is a wind force. And this is a pressure force. And the two forces balance each other, and at that point we have a new equilibrium, and that is the new equilibrium we want to calculate. Does it make sense to everyone that when the wind pushes the water, there's going to be high pressure here and low pressure here? Simply more water means that at a given level above the bottom, there's more pressure, right? Okay, you seem convinced. That's great. So a bit of a calculation, not too bad. Let's see how we do that. So first of all, what is the force by the wind? So the wind stress, tau is a symbol. The Greek symbol tau represents the wind stress. This is the force per unit area exerted by the wind on the ocean. So let's write here, force per unit area. and the area is the area of the surface of the ocean. So the total force is going to be equal to the size of the domain. So that's going to be L1, L2. I'll draw this in a second, times tau, where here's the Adriatic Sea. Say this one is L1. This is the width of the Adriatic Sea, so that's L2. So this is east and north, roughly. So the area of the Adriatic Sea is L1 times L2 multiplied by the force per unit area. This is the total force by the wind on the surface of the Adriatic Sea. That's the easy part. Now we want to calculate the pressure force. So for that purpose, let's consider a slice here. So here's the pressure force. So this is now up, and this is, say, north. And we have this sea level like this. And we're looking at a place here, and we're asking what is the total pressure that this surface feels. Then we'll have another surface here. So there's going to be some pressure in this direction, some pressure in this direction. The difference between the two would be the net pressure force on this slice. So let's start by calculating this total pressure force over the entire slice in that direction. So starting by right, the pressure itself at the level Z is equal to the density of water times gravity times H minus Z. And I want to explain that, but I'll give you a second. Okay, H is the height of the sea surface. So here's H. It's this thing right here. While Z is some level here. So we're asking what is the ocean pressure at the level Z? And it's basically equal to the weight of the water above that point, which is H minus Z. That's the distance of the column height of water times the gravity times density. That gives us the total weight above that point, and therefore that is the pressure due to the ocean, to the mass of ocean above that point. So now we have the pressure in one depth only, but what we need to do is integrate it all the way from the bottom to the surface of the ocean. So we need to multiply this by L2, so the total pressure force on the slice that we're considering is the width, L2, width of the slice, times the integral from the bottom of the ocean to the top of rho g h minus z. This is the pressure at the level Z times dz. So I'm integrating, the pressure is per unit area. So I'm integrating in one direction, and I'm assuming there's no variation in the cross direction, east-west direction of the Adriatic Sea. So I'm just multiplying by the width, and this gives me units of force. Force per unit area, which is the pressure turned into total force. And that's equal to, if you do the integral, 1/2 L2 times rho g h squared. Great. Now let's consider the force balance of this slice, but there's one more small step that we need to take. So consider again the geometry. This is north in the Adriatic Sea, south and up. And sea level looks like this. So we can call this delta H, and we can call this H. and the delta H is the result of the wind blowing in that direction. And I'm interested in the difference between the total pressure here in the north and the total pressure here in the south. That difference will be exactly balanced by the wind forcing that we calculated before. So we know what the total pressure is in this area. We just calculated here. So we need to take this expression evaluated in the north minus at the south. And that difference will be equal to the wind forcing. So let's write it here. Pressure in the north minus in the south is equal to the wind forcing. I can write it in the following way. 1/2 rho g h squared minus 1/2 rho g h plus delta h squared times L2. All of that is the net pressure force. It's the force, the pressure force on one side in the north minus that in the south. And that would be equal to minus rho g h times delta h times L2. So I actually want to correct what I said here. Let me correct that. So it's not that the pressure is equal to the pressure. Let's just say the sum of forces should be 0. So this should be plus this equals 0. So the correction is in red. The sum of forces should be 0 for this slice not to feel any net source and therefore not to move at all. Okay. So if we equate this with the pressure force, we're getting that tau L1 times L2 is equal to rho, the density of water, times gravity, times delta H times L2. So the conclusion, finally, is that the sea level rise, at which there's an equilibrium between the pressure force in the ocean and the wind stress, is equal to the wind stress times L1 divided by rho g h. That's our final formula here. Now we just want to understand this intuitively. Here.
Yeah.
I think that's a mistake. So this should be rho g delta h times L2. There should be an h here too. So let's correct that. And now we should be okay, I think, right? Great. That h came from that equation over there. Thanks for this. Okay, why does this make sense? Let's see. Obviously, if the wind is stronger, then you'll get more of a sea level rise in Venice. That's obvious, right? If the wind is blowing over a long distance, remember L1 is the length of the Adriatic Sea. So this is L1, and this is L2. So if the wind is blowing over a long distance, it also makes sense that this would increase the sea level rise. And the Adriatic Sea is long. Okay. So gravity plays a role, the density of water plays a role. H here. Why is this H here? Because it depends, the strength of the wind is distributed over the width of the depth of the ocean. So if the ocean is very deep, you'll have less of an effect on the net force balance and therefore on the sea level rise as a result of this. And you will, in the workshop, substitute numbers for this and see what the values are. And you can see how difficult is it to get a 2-level meter rise due to wind force, and it's not that difficult. I mean, of course, the wind would have to be somewhat exceptional. This happens once in 50 years, but still, it's possible. There's an issue with the Coriolis force and ocean currents that also makes a difference. I'm going to do this without equation in this case. I know that Lux is disappointed, but still. So here's the idea. The Coriolis force is the result of the Earth rotation. So any moving object relative to the rotating Earth will experience a force to the right of the motion in the northern hemisphere. So for example, here's a schematic of the Gulf Stream. The Gulf Stream is flowing northward. That's this arrow right here. And the Coriolis force is to the right of that. So that's this red arrow. But the Gulf Stream continues forward. It doesn't turn to the right. It doesn't turn eastward. And the reason is that this Coriolis force is balanced by a pressure force, which is drawn here in green. That pressure force exists because there's a high sea surface height here, low sea surface height here. So there's a net pressure force from left to right, from east to west. That exactly balances the Coriolis force to the right. So that says that whenever there's a current, like the Gulf Stream, there's going to be a sea surface height difference across the Gulf Stream, for example. For the Gulf Stream, it's about 1 meter. So if you cross the Gulf Stream about 50 kilometers wide, you're actually climbing up by 1 meter. That's a significant sea level difference. If the Gulf Stream gets weaker, then this low sea surface height will become larger, for example, or this high sea surface height will become lower. So if the Gulf Stream gets weaker for some reason, then the sea surface height changes as a result of that. So that's this balance between surface pressure, sea surface height and pressure, and the Coriolis force is a dominant contributor to sea surface height variations in many places in the ocean. Okay? If you look at the notes, the course notes, you'll see there's something called the geostrophic balance, which describes this in terms of equations. This is another schematic of the same thing. So this is a section. We see this is up and east. So we see the Gulf Stream flowing into the page here, the Coriolis force to the right, and the pressure force to the left. And you see the sea surface height shown by this blue line being high on the east side of the Gulf Stream and low on the west side of the Gulf Stream. And the difference, as we said, is 1 meter. And this force balance is what supports the sea surface height difference on the two sides of the Gulf Stream. All right. So changes in the strength of currents would lead to local changes in sea surface height. There's no causality here. It's not that the sea surface height is causing the Gulf Stream or vice versa. We can just say that they're in equilibrium. We covered atmospheric pressure, we covered wind stress, and we talked about how the ocean circulation changes could lead to sea surface height changes. Okay, getting to ice sheet melting. So let's see. This is a somewhat surprising effect if you haven't heard about it so far, I find, especially the magnitude. So here's a schematic. So here's Greenland. And suppose Greenland melts. You'd think naively that sea level that used to be here, used to be the thin line, would just move up toward the thick line, right? So ice is melting, the meltwater goes into the ocean rises. Turns out that that's completely wrong. What happens instead is that before Greenland melts, the sea level looked like this. It's tilted toward Greenland. The reason is that the mass of ice here has a gravitational attraction. It attracts the sea level, and therefore the sea level piles toward Greenland. Now, if you're melting Greenland, the gravitational attraction weakens. So yes, the average sea level goes up, but also the tilt is becoming weaker. So you see the new tilt. This is the old tilt is the thin line. The new tilt is the the thick line. And you can see that sea level around Greenland actually went down. So when you melt Greenland, globally sea level would go up because you're adding water to the ocean. But locally around Greenland, because we're weakening the attraction, the gravitational attraction of ocean toward Greenland, sea level in Greenland would go down. So here's what we're saying. This is referred to as sea level fingerprint or fingerprints. And So if we melt an ice sheet such as Greenland, we're adding water mass to the ocean, but the gravitational attraction of the surrounding water decreases on a fast time scale, obviously. And sea level decreases near the melting ice sheet, but rises more than the global in the far field. So here's a calculation. So what do we see? This is a calculation where Greenland melts, and the colors show you the sea level change, and white is negative here. So this means that all of this area experiences a decrease in sea level. So it's a distance of 2,000 kilometers from Greenland, roughly. You get a decrease in sea level. Of course, everywhere else, you'll get an increase in sea level. Here's the surprising thing. If Greenland melts to a degree that changes global mean sea level by 1 millimeter, so global mean sea level increases by 1 millimeter, the decrease near Greenland would be 10 times bigger. So you're increasing global mean sea level by 1 millimeter, but in the area of Greenland itself, the sea level would be decreasing 10 times faster. Isn't that pretty amazing? And I think we are done. So we'll see you next week. Thank you.